All right, it's just after 2 minutes after, so we'll get started. So welcome everybody to this webinar, the ATA webinar. I'm featuring optimization of TPMS heat exchangers using STAR-CCM Plus, NX and HEEDS. My name is Adam Green from ATA Engineering, and I'll be joined by Chris Stoich to talk about the technical parts of the presentation. So a few housekeeping things. We have everybody on mute for the presentation. If you have questions, please put them in the chat, and we will answer them either as we go or at the very end. And also, this webinar is being recorded and will be available on our YouTube channel, so you can share it with other colleagues if you want to later. So with that, let's get started. I'll just do a few slides and discuss ATA as a whole and who we are before we get into the details of the presentation. So ATA Engineering, basically we are the high value engineering services company, and we specialize in various industries. Really, aerospace and spacecraft are our main industries, but we work in defense, themed entertainment, and also some high speed systems. But really, the aerospace and the space part are really our main areas of operation, and we are very highly skilled group where we have over 220 full-time staff, and basically over 185 of those are degreed engineers. So you can see that we work at the very highest levels of engineering problems, and people come to us when they are struggling, and the kind of people who come to us are NASA, JPL, those kind of folk. So you can see we tackle the really hard problems. And we are based in 9 offices throughout the US. Our HQ is San Diego, but you can see where others are, and most of those are centers of aerospace activity in the US. Those with the little lock next to them are areas where we actually have secure facilities to do secure computing and research work for DoD and other sensitive areas. So we're very proud of that resource. And so overall, we're an ATA, I'm sorry, an employee-owned small business, which basically means that everyone on this call and who's ever working within the company are very vested in making our customers very happy. It's also a great place to work, and that means that we retain all our staff, a lot of our staff over the long term, and many of us have been working here 10, 20 years, really create a very great working environment. And so with that in mind, when you look at the history of the company, ATA was started in 2000, and obviously 2025 is our 25th anniversary. We're very excited about that this year. But we started back in as a division of SDRC, who'd been around since 1967. They created ideas, were involved with unit graphics. And so ATA has a very close history with NX and obviously now Siemens NX, where we do a lot of support for them, a lot of training, and really are very closely tied to Siemens and the NX story. And we became a Siemens VAR as we were using many of their tools in 2007. And by 2016, we became a gold partner, which is almost the highest level. And since then, we've grown to become platinum, but we've also added STAR-CCM Plus, HEEDS, and most recently, Siemens test and measurement hardware and software to the products that we sell for Siemens. So we are very closely connected with all of the Siemens SimCenter product lines and test. And so what do we actually do? Well, we do design analysis and test at the highest level, and really that is how we end up using so many Siemens tools, because they really fall into all of those buckets of usage. And we also do large amount of test services, really, from basically ground vibration testing is one of the major areas we focus on, but really many others: aeroelasticity, acoustics, lots of flight and test work that we basically have a large test team that either will do it locally or travel around the US and the world, in fact. And this is an example of a test glider that was actually instrumented in the ATA offices in San Diego. And it was interesting because it actually didn't fit. It had to go out the other door to actually get it in the building. So test is a large part of our business, and really was was part of the ATA original work that was done when they were within SDRC. But you can imagine that doing all of that, we use a lot of Siemens software, and we've become expert at using it. And so we sell it as part of the VAR business with Siemens. And we also have a lot of people in-house who are experts at it. So SimCenter 3D, FEMAP, Nastran, STAR, HEEDS, and AIMSIM, all of the SimCenter tools, together with NX and SimCenter 3D and TeamCenter are all SimCenter products that we support at a very high level within the Siemens group. And really, certainly on the STAR side, we have the most, I would guess, of any of the VAR partners for support. So we have a lot of depth on our bench to really give our customers great support when they're using the SimCenter tools. So with that, let's kind of move over to our subject matter today, and that is optimization of TPMS heat exchangers in STAR-CCM Plus using NX and HEEDS. And so this has come about from customer requests over the last few years of how they can optimize TPMS heat exchangers. And for those who are familiar with that, I'm sure most people on the call are, otherwise you wouldn't have attended, but they are basically heat exchangers that are very complex in their geometry, but they are, because of 3D printing and additive manufacturing, they can actually now be manufactured. Perhaps 10 years ago, it wasn't possible to manufacture them because of the complex nature of the geometry. But now with additive manufacturing, we can, and hence that gives us new challenges for design. It opens the playing field for much more scope in the design, and hence using NX and STAR and HEEDS, we can really explore that field with much wider to get optimized designs. And so, starting with the basics, I'm sure everybody knows this, but NX is it's predominantly CAD with some add-ons for analysis and so forth. STAR-CCM Plus is CFD, and HEEDS is a product for optimization and workflow automation, and it's really the kind of the glue that holds the first two together in this case. And so when we look at NX, why is NX kind of ideally suited to this? And going back a little bit, when you look at STAR-CCM Plus, STAR-CCM Plus has its own geometry engine. And hence you could almost do a lot of this work without using NX, just using STAR and HEEDS together. But NX brings to the table a lot of automated functionality for creating these TPMS heat exchangers parametrically, which is the trick, and has been a challenge for us here over the last few months working on this, because these geometries are very complex, and being able to create them automatically to feed into a workflow has been something that we've focused on a lot, and now we've managed to crack it. So we're very excited about that. So when we look at NX as part of this, basically you can see that the actual pieces within NX for the design for additive manufacturing really make it ideally suited for this case. The implicit design on the top left, if you had something more complex with lattice structures, you could add that. But really, it's the implicit design and the way that the geometry can be parameterized to create it that really makes NX ideally suited for this challenge. And STAR-CCM Plus, it's the premier CFD tool globally, and I don't think it really needs any explanation except that its capabilities let us do all of the physics in this heat exchanger problem. So the last piece here is HEEDS, and what is HEEDS? And so I thought I'd spend a few minutes just covering how that enables this project. And so what is HEEDS? This is the Siemens slide, discover better designs faster. But overall, what is it? It's basically a multidisciplinary design analysis optimization software and really does two key things very well. And that is that it automates workflows. And once it's done that enables it to do design space exploration. I mean, it has many, many tools to make both of those pieces both very, very fast and very easy. And so that's really the goal here, to automate a process where we can investigate the landscape of these designs, but do it in an automated way. And so when we look at HEEDS has part of HEEDS is called the HEEDS Workflow Manager. And really it's laid out like a flowchart that can be repeated. And so in this case, we've got products that are not all Siemens. We've got CATIA answer, STAR reporting results to an Excel file. And you can see that basically HEEDS is able to plug into each of these to control them, to run them, to interrogate results, and then make assessments and rerun them based on those results. So in this case, the CATIA's the geometry, ANSYS probably meshing, Abacus, JMAG, and STAR are doing some CFD work, and then some kind of internal tool. We don't know what that is in this case. And then Excel is probably just creating a report of the results. And HEEDS can look in all of those and really give you a picture of the best designs for this workflow. And then it can repeat the workflow. It can run this 100 times, 1,000 times, whatever's needed to get to a result that it feels is better. And so when you look at that workflow image, you can imagine that, okay, well, so HEEDS can talk to every product on the planet, and not quite, but it can talk to a lot of them, mostly CAE tools. And you can see there's ANSYS here, there's some Dassault tools, a lot of Siemens tools. Really any tool that is doing analysis, HEEDS can talk to using its own API. So if you want to control, SolidWorks geometry that's going to go into, say, STAR or any CFD tool, HEEDS can control it. So it really opens up the way you can design these things. You don't need to necessarily be a full Siemens house to be able to use HEEDS to wrap around your workflow. And it really makes it very flexible. And so those all sound grand things, but let's look at a quick example of how that might work. And so there's a company in Europe called ZF, pretty famous for automotive things and gearboxes. But in this case, they were looking at this control arm for a vehicle. And the goal in this case was we've got the CAD geometry. How do we make it as light as it can possibly be, but still satisfies all the load criteria? And so obviously automating this to create the right geometry and the right physical status basically is key here, and doing it as fast as you can. So when we look at the flow, this is basically the OEM requirements came in and it was created. And if in this first box here, basically 10 parametric slices were created in the geometry. And then those parameters are controlled by HEEDS. It goes into the geometry creation from there. The FE mesh and loads, linear stress, nonlinear, and fatigue analysis are all done as part of the HEEDS workflow until it comes up with a design that is both as light as it can be, but still satisfies all of the load conditions in these various simulations. And so this is quite simplistic. It's one part, and it's really doing FEA but extended, but it still highlights the idea that HEEDS can loop around basically any analysis loop and do things faster than you can do manually. And so if we look at the result of that, obviously HEEDS evaluated 1,375 designs and really got to this position of the lightest and strong enough piece in under 4 weeks. And it was estimated that ZF would have taken over 6 months to actually do it as a manual process. So it really highlights the point that, first of all, HEEDS can help you explore areas that you really couldn't get to doing a manual process. And also it can just do things much, much faster. So on the Siemens SimCenter side of things, HEEDS can pretty much reach across all domains, from system simulation to mechanical, CFD, and electromagnetics, all the way through to physical testing can be included in a HEEDS workflow. So it's interesting to think about the combinations that could be effective for any of our clients about which pieces of this could be useful. And so lastly, when we look at which pieces of HEEDS make it valuable, obviously this first piece of process automation is very valuable because it takes less time to do more iterations around a design loop. Efficient search is the optimization strategy. It lets you basically home in on the lightest, strongest piece available, and it has all of those algorithms built in. Most of those are not really tunable. They are tunable if you want to, but they also are automated so that they can just work straight out of the box. They're hybrid. They tune themselves as they go, and so the efficient search methods are very good at producing answers without becoming an optimization expert in your own right. So that's very effective. And then these last two on the right here, almost expected nowadays, but distributed execution. HEEDS can manage clusters. It can manage the cloud. If you want to send 100 jobs to an AWS instance, HEEDS can manage that for you. So that's very convenient in this modern day and age. And then lastly, all of the results give a lot of graphical representation of the results, so you can really dive into the different parts of the model that really govern the result. So you can see why something was better, why something was worse, and really then move on to the deeper analysis if you want to. So with that, Chris, I'm going to pass the ball to you to talk about using that style of workflow for looking at TPMS heat exchangers.
All right, thanks, Adam. Just gonna pull the share over from you. Adam, I sent you a request to share. Can you check to see if you have a little
Yes.
notification there?
I think I'll just stop my share.
Okay.
There you go. You got it.
Great, thank you. Great, okay, can you see my screen?
Yep.
All right, well, yeah, thanks, Adam. My name is Chris Stoich, and I'm going to present the optimization of TPS heat exchanger in STAR using NX and HEEDS. I want to give credit where it's due. Most of the work here was done by my colleague Evan Halls, and I just get the privilege of presenting this cool work. So yeah, over the past few years, there's been a lot of technical advances or technological advances in 3D printing, and it really allows the manufacturing of very complex geometries, which is great for heat exchangers where you do want to build something that has these tortuous fluid paths with a lot of surface area. In particular, what we're going to focus on today is the ability to 3D print these triply periodic minimal surfaces, or TPMS, heat exchangers. So I've got a few examples of different types of TPMSs on the right there. But now that we have the ability to create these complex geometries, I think it's really hard for, at least myself to understand really how is, changing one parameter or the other in these going to affect performance. So in the case of a heat exchanger, an optimal design may want to balance heat transfer and also pressure drop. We don't want to, get a bunch of heat transfer, but at the expense of, having to really force fluid through. We want it to be easy to pass fluid through while also, optimizing heat transfer. So how can we design one of these, or how can we choose a design that best balances these objectives? Well, this is where these Siemens tools come in. NX STAR-CCM Plus and HEEDS can really help us along the way, and I'm going to demonstrate that here. We're going to optimize one of these TPS heat exchangers to maximize heat transfer while minimizing pressure drop. So the story starts with NX. Adam alluded to the fact that NX allows you to produce these TPMS geometries using its implicit modeling tool. And it does this with just the presentation of a few different parameters. So in this case, we've got cell size. That's the size of one of these repeating cells in this kind of lattice of geometry, and then wall thickness, and then you've got a number of different types of geometries to choose from too. The one that we're showcasing here is the Schwartz type. And then also you define kind of a bounding box that's going to say how large is this array of cells going to extend. So These are all of these parameters can be exposed as parameter expressions, which can be used down the line in the optimization. And then as shown on the right here, we've got these hot and cold fluid inlets, and those are created by just using Boolean operations and subtracting those kind of straight fluid streams from the fluid streams passing through the TPMS. So the capabilities of NX to generate these implicit models or these TPMS geometries is seamlessly integrated into STAR-CCM Plus using the NX CAD client. So what this does is it really gives STAR-CCM Plus access to the CAD modeling engine within NX. You can see that in the figure in the lower left that the unit cell size and wall thickness expressions are made visible in the STAR-CCM Plus window on the right. So we can make changes within STAR. It uses the NX engine to change the geometry, which then gets updated within STAR. So now we move on to STAR. STAR is a multi-physics solver that has everything under the hood. It's got CAD, meshing, a large suite of high fidelity physics solvers, and then powerful post-processing tools. So in this case, we pull in that NX generated geometry, and STAR's automated mesher builds a mesh on it. And it does this creating node matched interfaces at the fluid solid interfaces to accurately capture heat transfer to perform the conjugate heat transfer simulations. We're using polyhedral cells within the volume, and a number of prism layers on the solid boundaries to capture accurately the temperature gradients there. There's, as I mentioned, a number of multi-physics capabilities. Here we're using RAND steady state flow predictions to couple the solid thermal predictions in this high fidelity conjugate heat transfer approach. And then there are a number of powerful post-processing tools. In this case, we're setting up reports to measure the temperature drop in each fluid stream, the pressure drop, the temperature change in each stream, the pressure drop, the associated heat transfer, etc. And then we can also look at scenes to really visualize the fluid flow and gain some insights into what is going on inside this complicated geometry. So STAR allows you to parameterize pretty much anything. All the fluid inputs are parameterized. So in this case, it's pretty simple. We've got two streams, so we've got the flow rate and the temperature for both of those streams. Also exposed to STAR, as I mentioned, are the CAD parameters through the NX CAD client. So in this case, we're varying that unit cell size and also the wall thickness. And then on the lower right, I'm showing monitors of some important responses that we want to keep track of. That's pressure drop through the two fluid streams, and then also overall heat transfer between the two fluid streams. I'm using a solution-based stopping criteria, which kind of waits for these monitors to asymptote. And so we're waiting for both of them to asymptote, so we know we've got a converged solution. And once we hit that convergence, we don't want to compute anymore. We want to move on to the next one. So this really, ensures accuracy while preserving computational efficiency. Okay, and so we've gone through NX and STAR. HEEDS kind of controls all of this. HEEDS will orchestrate this intelligent design space exploration really by just interacting with the parameters and solution monitors. It's kind of ignorant of the physics that's going on, but it varies parameters, looks at what the response is, and makes decisions from there. As Adam mentioned, HEEDS is set up to interact with a lot of different software. STAR has a particularly nice portal, which really facilitates effortless simulation setup and communication with STAR-CCM Plus. So once STAR is hooked into HEEDS through this portal, HEEDS really orchestrates the run, setting up parallelization, the initial condition, everything. And then, right, so HEEDS is through the parameter or through the portal also given visibility to the input parameters that we care about. Those are listed on the top right, so wall thickness, flow rate, unit cell size. We also put temperature in there, but we are not varying those in the optimization, but it just allows us to make parameter changes within HEEDS if we're interested in a different condition. And then below that, in the STAR makes visible to HEEDS, the simulation responses. So that's pressure drops, heat transfer, the temperature changes within the fluid streams. So once we push go, HEEDS uses this proprietary Mo-Sherpa algorithm for multi-objective optimization. In this case, I mentioned that the objectives that we care about are heat transfer. We want to maximize that, and pressure drop, we want to keep that as low as possible in each of the fluid streams. Some additional inputs that we can use to satisfy our optimization and computational constraints are, the number of evaluations we want to run. In this case, we ran 500 evaluations, so that's 500 different design instances, and archive size. Archive size is a little bit less straightforward. It really defines kind of the resolution of a Pareto front in a multi-objective optimization. You can also, weight objectives differently if we know we care more about heat transfer than pressure drop. And then also some smaller considerations like storage constraints. HEEDS can save the input files and results from every design iteration, but that can get pretty storage heavy, and so you can tell it, hey, I only want you to save the best one, or the ones that also failed, so I can look into those, and HEEDS allows you to do that. Okay, so here is kind of the orchestration of this optimization that we ran in HEEDS. This 500 design optimization ran over a weekend on just a desktop machine. You can see that 347 designs were successful, and there were 153 error designs. This is one of my favorite features of HEEDS because that it has this built-in fault tolerance, and I like this because I don't have to log in during the weekend and see if my chain of simulations was interrupted by one failure. I know that HEEDS is going to look at a failure and say, hey, this may have failed due to some impossible geometry that we asked it to create, or some cluster hiccup or something. Whatever reason it has, it's just going to say, okay, we're going to skip this one and move on, and progress through the optimization. And so that is excellent. Gives me a lot of peace of mind so that I can do weekend stuff and not simulation stuff. This particular job ran each case on 4 cores, and ran 2 cases in parallel. You can have it, you can change that configuration however you'd like based on your computational resources. And again, yeah, this ran over the weekend without myself or Evan worrying about it. And so once the optimization is done, HEEDS generates this Pareto curve. So if you're not familiar with the Pareto curve, it is the curve along which you can't, increase the goodness or improve one objective without, decreasing on the axis of the other objective. So here we point out a number of designs that lie along that Pareto curve, and each of those is, I guess, optimized for that particular portion of the Pareto curve. So it's really up to the engineer now to choose, okay, which of these optimal designs do I want to build, which satisfies kind of my requirements most. HEEDS, not only generates that Pareto curve, but presents a lot of powerful data analysis tools, so you can better understand the design behavior. For example, on the left, we've got a few different parameters here. It can tell us the importance of those parameters. For example, in these steady state analyses, it looks like the wall thickness doesn't do anything. So it's something we don't really have to waste brain power on considering anymore. You can also, take a population of solutions and create a surrogate model of that so you can visualize data relationships. You can also look at the relationships between parameters and see if there are any correlations here. This is pointing out that there are, rather large correlations between, pressure drop and temperature change of the various streams. And then also, obviously, there's a relationship between the temperature change of the cold stream and the temperature change of the hot stream, and that's the one that's flagged as an 82 correlation. One additional thing that I'd like to talk about that we did not use here in this project was the HEEDS AI simulation predictor. And so this could have accelerated our process even more. What happens here is that, each of these simulations that we ran for the TPMS heat exchanger, that took, some amount of time. It was a real simulation and took time. What the AI simulation predictor might have done is run, 100 simulations and then started building a model from that, from which it could start generating AI predictions to kind of fill in the gaps there, but much more efficiently. Along the way, it would continue to sporadically kind of solve the multi-physics problem again to kind of test the accuracy of the AI predicted solutions, but it really can save a lot of time and produce comparable results. In this case shown here, which is not heat exchanger, it's this multi-element airfoil. You save 45% of the computational time over these 800 design iterations, and you can see it generated this Pareto curve between lift and drag coefficients. So in conclusion, I hope that this has been compelling evidence that HEEDS can really help you optimize these complex geometries such as TPMS heat exchangers. NX gives you the ability to, through its implicit modeling capability, to define this complex TPMS geometry. The CAD client makes the communication between NX and STAR pretty seamless, and then STAR provides, very powerful meshing capabilities, very high fidelity models to solve the CHT problem. And then HEEDS, wrapped around all of that, kind of orchestrates everything and drives the simulation to an optimal, or sorry, just drives the design to an optimal result. So yeah, using this workflow, without a lot of manual uh, changes and decision points and stuff, you can really make design decisions in a number of hours, or in this case it was 2 days, and not weeks that it might take a human to do the same thing. Yeah, so that is the end of this presentation. I can take any questions.
Thanks, Chris. That was great. Just waiting to see if anybody has any questions in the chat. One thing I wanted to mention was that on the HEEDS AI predictor piece, could you go back one slide? So basically, HEEDS AI uses real simulated points to build an AI kind of machine learning model, and then it makes decisions based on that. But once it's made decisions, and if there's any points that turn out to be very good, it will go back and rerun those as actual simulations. So it's a kind of it's using AI, but it's using it in a very safe way because it's not as if a point that might be identified as optimal is only generated with AI. It actually goes back and does the full simulation. So just to make us feel confident that AI does work in this context.
Right. Yeah. Good thing to point out, Adam. Thanks.
So it looks like we don't have any questions. And last call for any questions in the audience. All right. Well, we appreciate your attendance. Thank you very much. Once again, this will be up on our YouTube site for you to review later or share with colleagues. So we thank you very much for attending, and we will wrap up for now. Have a good day.
Thank you.